touch off. All right. I mentioned a few times, I think, the concept of integration and differentiation, more than a few. And remember, we remember that the integral of a dt from time 0 to 1 is equal to your velocity if you start with a velocity of 0, and etc. down. What, of course, that is if we have a graph here of acceleration in time, if acceleration is positive, the area underneath that graph, if it was a constant, is just a times t, and it goes up from there. I've also pointed out Wolfram alpha, and I've also talked about the calculator. So we're going to look at this concept of just a simple load diagram where, in fact, the load is a constant, right? And then we'll also look at one where the load is not a constant, but it increases. And we'll think about the function, writing the load as a function of x. So in this case, the load is, we'll call this 5. We call this 5 up. And if this is 10 long, of course, this is 50, and this is 25 on the side. And we know that our shear diagram goes down, across like that, etc. And we'll also say this is W equals x. In other words, it goes from 0 to 10. And so from here it goes 0 to 10. Remember, it's in the middle there. And so now we're going to look at how that's done mathematically. And I'll start with Wolfram alpha and point out that, once again, we're using this as a gateway, if you would, into Mathematica, which would actually allow you to do the symbolage. So in other words, if you put in integrate x squared from x to 0 to without anything, it would probably give you just, I'm going to try that here. Let's say if you wanted to integrate x, the function y equals x, with respect to x, what does it give you? It actually gives it to you. So there you have it. So that essentially is the function that if you integrate x with respect. So it does that. That is called just basically an indefinite integral. So in other words, that's the function that describes the area underneath. Very often in engineering, you're trying to do a definite integral. So in this case, we're going to integrate when we know 5 with respect to x. In other words, y equals 5 is the function with respect to x from 0 to 5. And that should be 25. And that you have it. So that gives you a representation of the integral, basically. So how does it look like on a calculator? And we're going to see where that comes in a second here, if I can kind of do my pen thing on the right side here. Go to and do the eraser here. It starts to be, it comes in, it's always been here, just so you know. It was all the way through physics, it was all the way through soils, it was all the way through GPS, I presume. Not so much in survey, but even within surveys, you're doing things like best fits and the like, least square adjustments. So I'm going to go here, bend back to review, get my pen back on here. So let's look at a real basic. And of course, these are not basic, they're more than basic. Basic load diagram, one that we know. The load is a constant function W, okay? And it goes for a distance L with a pin joint here and a roller joint. And later on you'll see what the calculus does. It allows me to do a lot more than just these basic simple ones. Now I'm going to point out in Wolfram alpha, that's the difference in Mathematica. You couldn't do it. In Mathematica you could actually put in here W and it would give you an answer. I presume that this will not. It actually does, so it's actually getting better. It actually gives you the value, or if we give it an indefinite integral, it gives me Wx plus constant. So where does that come in? Well, if you thought about it, remember the initial the shear diagram. Basically, when we go back to this one here, if we think about the shear diagram begins at a reaction of WL over 2, and it ends then at a WL over 2 That's because it goes down with the slope equal to the opposite of the value. So that slope here is minus w equals the slope, right? And the area here turns out to be the area under the shear curve gives us the value of the moment curve. So the value right there is that area, which we know is w L squared over 8, if this is a distance L. So we know that. So how do we get that when we deal with integrals here? Well, if we start with the first integral, which is the integral under the load curve, you get to that, and now you can integrate this. And so this integral turns out to be w x with respect to x, and we'll see what we get for that. So it gets you that equation wl squared over 2, and what you miss then is some of this constant stuff, this definite integral. So that's basically how you go about using Wolfram alpha to do a whole bunch. And what you see here is it's actually a great idea usually to do the definite integral from 0 to 10. And it does mathematical integration. Now if I give that a value 5x, which is what we started with, 5x, we get something like that, and that looks like something like the shear curve. Again, remember, the shear curve is a subtraction from a number, so it's one graph minus another. So this actually is going to be a graph of the shear going from just that support minus that graph. But I just want to introduce you to those tools, and we're going to try one the opposite since we talked about it, and that is differentiate. And we'll try this now, x squared with respect to x, and we'll see how it does on that. And it does. I'm not sure what it did. Oh, because I said 2. Interesting. It's giving you more functionality in here. Differentiate x squared with respect to x. And it's 2x. Or how about this now? Differentiate the sine of x with respect to x. And it gives you the differentiation. How about if we put time in here? And so you see, how about if we went from 0, I presume, to pi? And it's giving you something that I don't even recognize, to tell you the truth, but it does do most of these functions as I'm going through here. So I'm going to go back to, it might not even, it's knowing sine t. So that's the differentiation, differentiate and integrate. On the calculator it looks like this. I'm going to go over here and turn on the calculator, hopefully, and I'm going to go and put in a function here. I'll put the function y equals 5. And there actually is a differentiate and integrate function in the functions. I won't be covering that here. I will do that once before the end of the semester, but again, pointing you towards Wolfram alpha and its ability to get you to some higher order math concepts which are standard order in engineering. Especially here when you finish walk away, are either disgusted, disgruntled, or whatever. This integration of load, shear, moment, and then integration of the moment curve, and then once again getting you to the actual shape of the equation and applying boundary conditions is kind of a capstone in that it takes you back to the acceleration and the kinematic equations. And so you can kind of start to really look at what these curves mean and what the integral mathematics means. It goes back to stormwater, it goes back to many things. So if I put in the function here, you remember y equals 5, I can now hit graph, and I don't have anything set up, but I can just go y equals 5, and I can say second calc, and I can calculate the integral, and it'll give me ask me for a lower limit. I'll say the lower limit is 1 and the upper limit is 3, and it'll give me an answer, and the answer was 10. That makes sense. I can go back to here and go back now here. Y equals 5 x, go back to second calc, I can integrate from lower limit of 0 to upper limit of 5, and it gives me a calculation. Now my graphs, you can't see it. So that's differentiate and integrate in a calculator, Wolfram Alpha, and conceptually. Thanks for listening.